Hello and welcome to this lecture where you are going to understand multilayer perceptron or multilayer neural networks. Last lecture, we dealt with linearly separable and non-linearly separable problems. We saw that we need more complex architectures to deal with more complex problems, such as the XOR operator. The single-layer perceptron can be used for simple problems. However, most commercial applications are non-linearly separable, so you need to understand the structure of multilayer neural networks. A multilayer neural network is very similar to the single-layer perceptron. There are the inputs x1 and x2 in this example, and it still has the sum and activation function. After applying the activation function, the output of the neural network will indicate a prediction. The same you learned for the perceptron. The big difference is that there is an additional layer of neurons between the input layer and the output layer, which is called hidden layer, as you can read here. Something that is also important is that the sum and activation functions are applied for each one of the neurons in this new layer. Each of the inputs is connected to each one of the neurons in the hidden layer. For example, X1 is connected to the first, to the second, and to the third neuron of the hidden layer. Similarly, X2 is connected to the first, to the second, and to the third neuron of the hidden layer. There are 6 links between neurons, and each link is a weight. So, there are 6 weights connecting the input layer with the hidden layer. For each one of the 3 neurons in the hidden layer, we are going to perform the same calculations as the perceptron. For example, for this first neuron, we will multiply the value of x1 by the weight w1, x2 by w2, apply the sum function and the activation function to have the final value. Then, we send this value to the rest of the neural network. This process is called feed-forward, which is why this type of neural network is called feed-forward neural network, because information flows from left to right. We can notice that the 3 neurons in the hidden layer are connected to the last neuron in the output layer, and there are 3 new weights, and the same calculations will be applied until the final output is returned. To deal with complex problems, we need different activation functions, since the step function is quite simple. Here you can see the sigmoid function, and the values are in the range from 0 to 1, in the format of letter S. The maximum value is 1 according to this upper line, and the minimum value is 0 according to this bottom line. The blue line touches all the points on the graph, which is why we can say that it returns values in the range from 0 to 1. Here you can see the equation to get the sigmoid value. If x is high, the value is approximately 1. And when I'm talking about x, it means this value in the equation of the sigmoid function. If you send the number 50 to this function, these mathematical calculations will be performed and a value between 0 and 1 will be returned to place the number 50 in some point within the limits of this function. If it is a high number, the value will be positioned at the top of the graph. Otherwise, if x is a small value, the result will be approximately 0. So the number will be positioned at the bottom of the graph. This function does not return negative numbers, and the letter E in the equation indicates the exponentiation mathematical operation. If we consider number 50, for example, the exponentiation of this number will be made here. Now let's see the calculations step by step. We will consider now the XOR operator. If x1 and x2 are 0, the expected output is 0. x1 0 and x2 1, the expected output is 1. The third row, x1 equals 1 and x2 equals 0, the expected output is 1. And finally, if x1 and x2 are both 1, the expected output is 0. The goal is to find the best weights to classify the XOR operator. And as I said before, it is not possible to solve this problem using the single layer perceptron, since this is a non-linearly separable problem. Let's move on to the calculations. You can see the first row 0 and 0 and see that there are 9 weights from the input layer to the hidden layer and from the hidden layer to the output layer. And something important to say is that when working with neural networks, the weights are randomly initialized. The first step is to apply the sum function, the same you learned before. So we will take the first neuron of the hidden layer, input times the weight, 0 times minus 0.424 plus input times weight, 0 times 0.358. The result is 0. So we have here the sum equals 0. Now we move on to the next neuron. Input times weight plus input times weight. As you can see here, the result is also 0. Now we move on to the third neuron of the hidden layer and apply the same calculations. Input times the weight plus input times the weight. The result is 0. Now we need to apply the activation function. It is not the step function. Now we are going to use the sigmoid activation function. I'm not going to show these calculations step by step. I will just put the result here. When we send 0 to the x parameter and applying this equation, the activation value will be 0.5. Now we need to send the second value. The activation is also 0.5. And finally, 0.5 to the third neuron. This is the first part of the calculation. We can put here 0.5, 0.5, and 0.5. Now we need to move on to the next row, 0 and 1. We can see here the inputs and all the calculations are already performed. The sum function and the activation function for the first neuron, for the second neuron, and for the third neuron. I encourage you to pause the video and check all these equations. If you want, you can open the calculator just to make sure the values are correct. Then we need to go to the next row. See here, 1 and 0. This is the third row. We apply the sum function. You can see the calculations here, and the activation function. Finally, we move on to the last row, 1 and 1, and apply the same calculations, the sum function and the activation function. The goal of this step is to get the values here, the results of the application of the sigmoid activation function. The calculations from the input layer to the hidden layer are complete, and now we need to perform the same considering the direction from the hidden layer to the output layer. See here that we are getting the first row of the dataset, 0 and 0. And these values are the results of the sigmoid activation function. Let's perform the calculations regarding the sum function. It is the same we applied before, 0.5 times the weight plus 0.5 times the corresponding weight plus 0.5 times the corresponding weight. The result is minus 0.381. So this is the sum function. Now we need, again, to apply the activation function. When we send this value to the x parameter, the result is 0.406. This is the prediction of the neural network for this row. We are expecting 0, but the prediction was 0.406. Now we can go to the next row, the second one, 0 and 1, as you can see here. All the calculations are already in the slides, and again, I encourage you to pause the video and check the values step by step, so it will be easier to understand. The sum function and the activation function, 0.432. The prediction of the neural network for this row was 0.432, and the expected output is 1. Let's move on to the next row, 1 and 0, as you can see here. And the prediction of the neural network is 0.437, and the expected output is 1. Finally, let's move on to the last row, 1 and 1, and we can see the corresponding results. The activation or the prediction is 0.458, and the expected output is 0. That's all for these calculations of the multi-layer perceptron, and in the next lecture, you are going to learn how to calculate the error. See you there!